Good evening, morning, lunchtime, afternoon, take your pick. Welcome from wherever you are in the world to Ask Tom Office Hours, coming to you from India today. Hopefully you can hear me. It might be a bit quiet because I'm traveling at the moment on the Yatra tour, which we'll talk about shortly. I'll give you a quick look. That's the very effective microphone setup there with the kettle and the microphone on top. So as you can imagine, we're doing things a little bit on the what we can find in the hotel room concept here. But hopefully you can hear me and hopefully you can see me. Hopefully that's not a message in the chat already saying, I can't see it. No, thanks, Dennis. Thanks for letting us know. As I said, I'm here in Pune. I'm part of the Yatra tour. Before I talk about that, for those who have never been to India or hopefully keen to come one day, I thought, given that I'm in a hotel room, I'll give you a quick look. So let's poke this out the window. Hopefully I won't pull the laptop off the thing, but there we have Pune out the window. So Pune is, as you may have seen in the north on the map, if you join, it's sort of halfway up India. It's getting toward the north side of India. Beautiful place. We're doing an event here tomorrow, and we've been on the Yatra tour, but some of the weather's been rainy, some of it's been hot, but most of it has been absolutely lovely, especially coming from my Perth wintertime. Hopefully it'll sort out its exposure there. Let's get that sorted out. Oh, I'm a bit washed out. Hopefully it'll sort itself out as we go. So welcome to this office hours session. Let me share my screen and we'll just have a look at what we're actually going to talk about today. One moment. Okay, getting in touch with me is very easy. I used to put various links on how to get in touch with me up on there, but the reality is, with the way the social media is going, it just got out of control because there's blog, there's email, there's Facebook, there's LinkedIn, there's Twitter, there's Instagram, there's you name it. So I came up with an easier way of just having a linktree.connor piece of information there. And what we've done with Linktree is if you go to that website, what you'll then see is easily clickable links to all the other ones as well. So hopefully that'll make things easier to actually see what's going on. Someone's put something in the chat, but I can't see it because my chat window's dead. So hopefully it's not something super important. Everything's fine. Someone's saying what the weather was like. Oh, weather in Israel. There we go. There we go. I like it hot. So I must say I'll be keen to get back to Israel, hopefully next year. I'll be submitting soon for that event, but I digress. As I say at the start of every Ops Hours, you'll see all the content in the slides is generally down to the bottom left. That's simply because when we run these sessions, we put them on YouTube afterwards, and we want to be able to put the speaker, in this case myself, in the top right corner, and that way hopefully you get a better office hours experience. So no need to worry if all the slides look down to the left. A few bits and pieces before we get underway with the technical questions. The first one is obviously just a moment of sadness. For any people from England on the call, you are having a fantastic week. For any country that plays cricket that isn't in England, which is particular the Indian audiences here and the Australian audiences, and in particular the New Zealand audiences, we're all pretty sad. So that's the first bits and pieces. It's been a sad week, but hopefully this session will reinvigorate us all. On to technical stuff. There was no office hours last month because I was at Kscope. One of the fun parts of Kscope was Alex Norton and I had a battle on which was the best SQL syntax, the Oracle derivations of things like joins and decodes, etc., versus the ANSI standard of things like left outer join, right outer join, natural join, the case statement, etc. Somewhat sadly, the audience vote came down to a 2-to-1 win to Alex. So there I'm knocked out on the floor, but we had a lot of fun. But the message was fairly consistent all the way through. That is, get the most out of the Oracle SQL engine. I'll spend a couple of minutes on what I'm doing here in India, because if there's any people who are speakers on the call or potential speakers, or even people who reside in India, I thought I'd talk about the Oracle Groundbreaker Yatra tour. Yatra is a Hindi word for journey. And A journey it certainly is. What we do is we run a 10-city tour of India, trying to reach out to all the communities. India is a obviously large country, and while there are the very large events at the end of the year, such as the Sangam event, which invites people from all over India and all over the world to come, it's like a conference equal to or larger than the size of things like Kscope and UK OUG. We also want to reach out to those people in India who can't make that journey. And so what we do is, rather than them come to us, we try go to them. And you can see there that we actually started, where's number one? We started in Chennai at the tail end of last week, and we've been jumping around with flights and soon bus rides, etc., to try to do 10 cities in 14 days. So if you're a speaker that's keen to really test yourself out, sign up for the tour next year. But for anyone that's not, as you can see, the tour is still in process. We're on city number 4. I'm in Pune, which is, as you can see, about halfway up India on the west coast. We got more cities to go, and please follow the hashtag OG Yatra. We've been getting really stuck into that. And one of the really nice things is we've been actually seeing a lot of people who are joining Twitter in India for the first time. Twitter's nowhere near as popular as it is in India is in other countries, but a lot of the new followers I've seen on Twitter all have joined July 2019. So it's great to see the world community getting closer together in terms of their community. One of the cool things that you have in India is it's a really strong bond between speaker and audience. And what tends to happen is, unlike many other countries in the world, the moment the talks are finished, the audience comes up, we all have selfies, we chat, we have good networking, good question and answer. And one thing that has become a tradition in India is at the end of the conference, we try to get as many attendees as possible into a single selfie. So here's a challenge for you. If you're running a user group event or attending one in the next few months, wherever it is in the world, see if you can get this tradition going. I know the Apex guys, when they held events, they try to get a photo of the entire audience with their hands up and yelling at Apex. I'm sure that could be molded into something where it's a selfie as well. But if you're running any kind of user group event, try to get a selfie, put it on Twitter, and that way it brings us all closer together. These are the questions that have come in. Some of these are from, I won't say last month, 2 months ago, because we didn't have office hours last month for DBAs. And some of them are new. We have 19C, best effort standby. I'll elucidate on that shortly. Random unique numbers, which obviously is sort of a contradiction in terms. 19C automatic indexing. There's a lot of buzz around the internet about that, and I had some questions on that, which I thought I'd talk about. Career advice. One of the things we've been doing here in Yatra on this tour is there have been dedicated sessions for university students. They've been invited to come along for free to all the tech sessions. But even if some of the topics there aren't really appropriate for people who are just getting started in IT, what we've been doing is having a separate track where literally myself and Sandesh Rao, who's one of the Oracle product managers or VPs, I think now, we pretty much sit at the front of the room and we say, let's talk how the IT industry works. So trying to get our perspective of many years experience into what the IT world is like for a graduate coming out into the workforce. So we had a question on that specifically on the office hours session. So I thought I'd treat that. I'll probably do that right at the end because I could talk for hours on end about that. So better to try cover the tech stuff first, and then we'll finish off with that if we have time, and hopefully we will. Memoptimize clause, we'll talk more about that. And hopefully a fairly simple one, which we'll get to, is data pump DDL only operations. This one came in, and even though I could probably point them at an Ask Tom answer that exists, it's important for me to, if people put office hours questions on, they take the time to make those questions and type them in, then we should treat them here during the actual hour if we can. So let's get on to question number 1. Best effort standby. Now, if you look in the documentation, I don't think you actually see any words along the lines of best effort. And so the actual question that came in from a poster was, I was at a user group meeting and the term best effort standby was mentioned as a new feature. I could not find such a term in the documentation. What is it? And I also went looking at the documentation and couldn't find the term best effort. However, I did find some various blog posts out there on the internet, and what it seems to be referring to is some of the enhancements to standby database that has come in Oracle 19C. So we thought we'd cover it off, and hopefully that is what the person in the user group was referring to when they said best effort standby. Here is your conventional primary standby setup. For those that aren't familiar with DataGuard who are on the call, we have a production or primary database. It doesn't have to be production, but it's obviously a database of some importance, because generally it's those databases that we want to have a replica of, kept up to date in near or exact real time. And that's what our standby database is. And obviously we dispatch redo logs to keep all the changes from the production database over to the standby to keep it in sync. And that's the key term here. We send redo logs, a list of all the changes that have occurred, over to the standby. One of the things you can do in an Oracle database is perform operations without doing logging. And obviously, in such an example, in such an instance, that leaves a bit of a gaping hole in your standby database. The standby doesn't receive some redo logs for an operation that has occurred on the production system. Now, obviously, if your standby database is a piece of mission critical infrastructure, something that you're going to rely on in the event of a disaster, then that's a bit of a problem. To resolve this, way back in Oracle 9, we introduced a facility called Alter Database Force Logging. And as the name suggests, what that does is any operation that has been requested not to generate redo logs is simply ignored. We still perform the operation, but we will use the redo logging mechanism anyway. So operations such as direct loads and etc. that can have the option of not recording their changes in the redo logs for performance reasons. If a database administrator has set Alter Database Force Logging, it doesn't matter. We will generate the logs regardless, because what we're saying is that we're saying the integrity of the standby database is more important than any performance benefits we could get from not generating the redo logs. And there's a very good reason why DBAs do that, because most of us have been in that scenario where redo logs get out of sync in some way with our standby, and we're left with a standby that is just a giant mess, at which point you're now in a position where that standby has to be fixed. And in earlier releases of Oracle, that was a real nightmare, because if you had a 400 gigabyte, 400 terabyte, 400 petabyte database, size doesn't really matter. You had to actually reclone the entire database to your standby. Given that standbys are often used for disaster recovery, they may be in a different data center, a different country, different continent. And as a result, sometimes the network lines between those really weren't designed for a recloning operation. Solving no logging issues could then be improved by copying just relevant data files that had no logging operations on them. That came in I think, maybe Oracle 10, where you didn't have to copy the entire database. You can simply copy the affected data files, and the DataGuard operations were smart enough to then perform a recovery and bring the database up to date. Before I talk about best effort standby, one thing I should note is that's even easier in, I think, 12.2, might have even be 12.1 onwards. If you do have a standby which in some way has got out of sync or messed up compared to its production, even if you had force logging turned on, then there's actually a very easy RMAN facility now you can use to solve these problems. You simply connect to the standby as the target. Normally we connect obviously to the standby as auxiliaries when we're instantiating it. In this case, the standby is the object of interest, for lack of a better term. So we connect to the standby as the target. The primary is actually the auxiliary. It's the source that we're going to be using to sort things out on our standby. And as you can see, it's just a nice one-liner command. Recover database from primary, and the database itself and RMAN will work out where the problem data files are, go get them from the primary, apply the appropriate archive logs, and bring your standby back into sync. So that in itself, while we're not talking about best effort standby, that in itself is a cool facility that not many people are aware of. It's very cool. And if you're looking after standbys, have that command in your toolbox in case you ever need to reinstantiate a standby without having to do a lot of manual work or copy the entire database again. But on to best efforts. As I said, being able to force logging in all cases is actually a pretty cool insurance policy for DBAs. They don't have to worry greatly about no logging operations being a cause of problems in their standby database. The problem is, what about those databases where almost all the activity is big, heavy-duty loads? And a classic example is data warehouses. or even in non-data warehouses, your average, let me start again, even in non-data warehouse databases, there are now large components of large bulk operations. With the advent of 12.2, where a lot of objects can be moved online with no interruption to service to give performance benefits, it would be nice to be able to do those as well without having to have the overhead of logging. And the only reason it's there is because we don't want our standby to be messed up. Wouldn't it be cool if we could have our standby in sync and still be able to do no logging operations? That would be ideal for things like data warehouses, but also some benefits for standard operational databases as well. And that's exactly what we have. I'm just moving my screen so I can see my syntax. We now have 2 additional facilities in Oracle 19c, which gives you, for lack of a better term, your cake and you can eat it as well. The first one is this one. It says Alter Database set standby no logging for data availability. I've put there in big blue letters, deferred commit. Let me explain what this option does in relation to a commit. I will now permit a database to allow no logging operations and to have a standby database, and also guarantee the standby database is kept in sync. That almost seems like a contradiction, but the way it's done with this syntax is to say a no logging operation has been done on the production database. I will not allow the commit to be deemed complete or successful until I've transferred those affected blocks over to the standby and put them there as well. You could think of this as the equivalent of doing a manual operation of doing no logging operation on the primary, somehow manage to connect to the standby, do that same no logging operation in the exact same format, and then commit and say, yes, I want both of these to be done. So this will slow down your commit processing, but that's not normally a big drama because, let's face it, big no logging operations generally take a long time anyway. That's what they're designed to do. They take a while to run. They're just a lot quicker than a logged operation. But what we do is we then, while that's going on, we send the no logging affected blocks to the standby. When all of that is back in sync, now we allow the commit to occur. Our standby is kept perfectly in sync, and we got the performance benefit of a no logging operation. That's pretty cool. That might not be ideal though if your standby is a long way away, for example, over a thin network line. I might do a gigabyte of no logging operations on the primary, and now I've got to wait for that gigabyte of blocks to be sent across this thin network to a standby, say in a different country, and I can't commit until that is done. I might be prepared to actually have a momentary sort of diversion between my standby and my production system so that I can get my commit done faster. And we allow that syntax as well. And that's this one. Alter Database set standby no logging for load performance. That is deferred transmission as opposed to deferred commit. So in that instance, what we're doing is allowing a no logging operation to occur on the primary. You then commit and we say, yep, we're done. Just like a normal no logged operation, you can commit it as soon as it completes. Now, of course, the standby doesn't have those no log blocks yet. In the background, we will start transmitting those no log blocks across the line and applying them to the standby in conjunction with effectively the redo logs. What that means is if you were to have a catastrophic disaster during that period, yes, you could have your standby slightly out of sync. You could have data loss, but that is the choice that you get to make. You get to defer the commit, or you get to say, I'm prepared to allow the commit to be fast, defer the transmission, and run that small risk that during that time frame when the standby is catching up, that there is that discrepancy between the two. I like this in the fact that now we've got a sort of a sliding scale of how up-to-date and how critical your standby is. If your standby is the mission critical part of your operation, then you do Alter Database forced logging. Don't let any no logged operations occur. If you're prepared to impact your primary from time to time, but you've got to have that standby in sync and you want the benefit of no logging operations, you can do deferred commit. If your standby is perhaps used for things like performance testing, application deployment testing, it's not a true DR, or DR is not its primary purpose, then maybe you could choose deferred transmission. That confidence that the blocks will get there eventually without having to do a lot of manual intervention, but accepting the risk that for a small amount of time, your standby is potentially out of sync with production. So it's a nice sliding scale now of features that are available, just once again, making your standby database more powerful and more useful. I will say one thing on that though. This is a question I've been asking at the various cities here in India in terms of standbys. I'm amazed by the number of people that do not have a standby database for their production server. Now, the response to that is often, well, disaster recovery is done by some other means. We have a site-wide mirroring on our storage arrays, et cetera, et cetera. There's lots of other means of having disaster recovery solutions. Even if a standby is never to be used for disaster recovery, you don't even have disaster recovery requirements, let's say, I still think every production database should have a standby copy. Let me explain why. The cost of doing that is zero. Now, that's a brave statement. The reason I stress that is almost no one, in fact, everyone I've asked on the tour so far has said that not a single customer out there with an Oracle database has one database running on one server. It just doesn't exist. You have development database, you have test databases, and obviously most of us have multiple production databases. So you've already got, by definition, at least two pieces of hardware running Oracle in your organization. One of them might be running production. In fact, for every production database that's running on one piece of hardware, the trivial thing is you can have a standby copy of that production database on one of your other existing pieces of hardware. By definition, that other piece is already licensed to Oracle. The standby cost in that in terms of licensing is zero because that box is already licensed. Now, obviously, I'm not the official licensed spokesperson for Oracle, but in my opinion, that gives you enormous flexibility to have a standby database. You simply put it on another system that's currently running Oracle. If you have no need for DR, why would I want a standby database? Well, given the technology, which we won't spend a lot of time on, called snapshot standby, what this gives me is a production database that can be opened read-write. It's totally isolated from the true production database. It's read-write. I can do testing. I can do unit testing. I can test out dbms stats commands. I can use it for taking backups to off. There are so many options to explore your production database in total safety, to take load off your production database in total safety for effectively zero cost. Now, you might be thinking, if I've done that, if I've broken the link with production, have I jeopardized my true DR? Well, not really, because even when you open a snapshot standby in read-write mode, the archive logs are still being transmitted from the production node. So you have a longer outage time if you do need to do a site-wide failover, and automation of that becomes a bit more tricky. But for that small inconvenience, you now have a regularly available full copy of your production database that can be trivially resynced with the true production. And what's not to love? There's so many options available to you that you can explore as a DBA or even make it accessible to developers. That's pretty cool. Enough ranting by me. That's number one. Well, man, the hour goes fast, doesn't it? Random unique numbers. Let's have a look at this. I need to generate random numbers for an invoice number, but they must be unique and must not overlap with existing values in the table. How can I do it? Let's get one thing out of the way first. For me, implementations like this are generally a recognition of the fact of a misplaced fear. And that fear is of sequence numbers. The trivial solution to this obviously is use a sequence, guaranteed unique, no issues with cross-session concurrency and stuff like that. And it's the object in the Oracle database that has been designed for generally precisely this purpose, to give you a contiguous set of unique numbers that is incredibly performance based. However, having said that, we often get people saying, I don't want sequence numbers. The invoice number in this case perhaps can't be guessed. We don't want to see something that's nice and sort of contiguous. Even that can be solved with sequence numbers by burying it, for example, in a set of random digits, but having the sequence values interspersed such that you still get that uniqueness. But putting that aside, let's come up with a way of perhaps trying to solve this problem. And to do so, we're going to run a little script. That'll be our first little demo for today. I'm going to take a different approach. This person said, I need invoice numbers that are always going to be random. The cost of just getting a random number and seeing if it exists in a table is actually quite expensive. Now that may seem strange. I just use, for example, dbms random and then do a query. That's not actually good enough because there is no guarantee that two sessions might not get the exact same random number. They might both then query the table to see if it's there. They'll both be told, no, it doesn't. They'll both then do an insert and one of them will block. That's a locking issue, which you obviously don't want. Sequences solve it, but if we're using a random number generator, we always run that risk that two people will get the same random number and we have a blocking issue. We can't just do a select for update because there's no such thing as that row yet. If we're both trying to insert, the row doesn't exist yet. Now we have to look at building some artificial synthetic locks using something like dbms lock before we do the inserts or lock the entire table. All these things involve complexity and either or concurrency issues. So I thought I'd tackle it in a different way, and that's what our demo is going to look at. Rather than generate a random number, see if it exists, why don't we generate all the random numbers first? We can do that as a one-off exercise. And what I've got here is I've got a table here which I've generated. You can see it's a global temporary table called GTT. And I'm simply doing select. The particular preference of this question was they wanted an R prefix, but really it's just a random number with an R prefix. And I've picked 100,000 rows and I'm ordering them by dbms random.value. So the values I'm actually creating are just the normal integers from 1 up to 100,000, but I'm sequencing them in random order, and then I'm going to read them off in that sequence in order to get random invoice numbers that are guaranteed to be unique. So let's have a look. I'm going to create a table called T, which is going to be our true table of random invoice numbers, and I'm going to use that global temporary table I just created as the source of those random numbers. So we insert in there, I can see I've created 100,000 rows. I'll gather some stats. So let's look at some sample data. Here's the first 10 rows. And we can get an idea of what we've done here. The tag or the invoice number in this particular demo is actually the digits from 1 all the way to 100,000. So by definition, they're all unique. But because I sorted them in random order, you can see they appear in, as you can imagine, random sequencing. The first one is 31090. The second one is 14427. The idea is just a unique primary key that goes from 1, as you can imagine, to 100,000, which is an easy way of identifying them. So if I was to read the data in ID order, in terms of generation of invoice numbers, I actually get random invoice numbers. I simply get 31090 first, 14427 second, etc., until I've exhausted all 100,000 rows, but they are by definition unique because I generated them using row num. But what have I gained here? Obviously, if two sessions go and pluck the first number off, ID number 1, then we're back to the same problem. They both got 31090. They both try and insert it. We have a blocking problem. What have we achieved? What I can do is, obviously, as I suggested, is not something like this. If I just do select for update, even that doesn't solve the problem. Session 1 would grab that and say, do select for update. Session 2 would come along and say, yep, go get the first row as well. Yeah, for ID equals 1, select for update, he would block. We had this same issue. I might need to fix as the sun goes down here, I get darker and darker in the room, so I'll have to fix that as well. Dynamic lighting, here we go. Who says I'm not an RT professional? Let's lighten me up a bit. There we go. So let's roll back that update. Let's look at the solution I'm looking at here. It looks a little bit complicated, but we'll walk it through. What I'm going to do is on line 8, I'm going to open a cursor using an index hint and the first rows hint to make sure that we use the primary key index so it's nice and efficient. There'll be no scanning here. I'm going to go get the very first row from the table where row num equals 1 for update skip locked. What that will do is, if I'm the first person accessing this table, I'll get ID number 1 and I'll lock that row. Then what I'll do is, assuming I found a row, I do a fetch on line 13, and then assuming I found a row, I'll then delete that value from the table. So I've grabbed ID number 1, which was R31090, and it's mine. I delete that from the table. No one else is going to be able to use that ever again. And I'm good to go. Let's now assume that's happening and a second session logs on and they want to do the same code. They'll run this exact same piece of code. They will do OpenRC, the same ref cursor on line 9. They'll look for row num equals 1 for update skip locked. row number equals 1 says, go get me the first row on the table, which will also be ID number 1 because I've yet to commit it. So I will actually see no rows in the second session. I'll be told there were no rows available where row number equals 1 that were not locked. I simply skipped that one that I actually saw because someone else had it locked. I'll then fall into the RC not found, as in I will simply close that cursor. I got no rows, I gave up. But you can see way back on line 6, this is actually a looping structure. The second session will try that 10 times before giving up and then eventually falling into an error. I can obviously choose how often I do that, and I can choose the amount of time I might choose to sleep between that. But what I'm doing is, as all other sessions will simply be able to continue working, they will simply not see that record until the first session commits. This solution, let's give it a run. You can see this session picked out 3190, and he will then go get the second row, 14427, etc., and it continues on. That will probably work in extremely high frequency application environments, lots of transactions where they commit almost straight away. And that is the likelihood of a second session not being able to find a row in 10 iterations of a fetch is incredibly low. It still runs that risk though, that eventually, A, you're burning a lot of CPU, and B, you might eventually fall through and actually get these errors. So I thought we change it to actually doing something a little bit more robust. And this is effectively how advanced queuing works as well. The second example is a little bit more robust in the sense that if I look at line 6, I'm now going to get 10 rows from the table without locking them. I'm simply using that same index hint to simply get 10 rows from the table. In this case, it'll be ID 1 to 10. Then what I'll do is for each of those 10 rows, I'll do the exact same logic as I had before. For the first ID equals 1, I'll do a select for update. That's on line 11, line 11, 12, and 13, and try lock it. Session 1 will likely get that row. If session 2 comes along, they'll also get a looping struct. They'll basically get the first 10 rows from the table. Then they'll try incrementally, try lock the first row. I don't get that because session 1 has it. Try lock the second row. Oh, I got that row because no one else had locked it. Session 3 would come along, get the first 10 rows from the table, and end up locking the third row, etc. So now I've increased the likelihood of multiple sessions being able to get a row and without having to continuously loop around. So it should be more efficient and also gives me a little bit more insurance policy if a session happens to hang on to a lock for a long, long time. So that's the complete solution that I provided to this person, really just to explain the way skip locked worked. That's really what the objective was here. So I'll give this a run. Same thing, he got 31090, 14427, and so on. And multiple sessions would achieve the same result. But my overriding goal for this one really was to talk about skip locked. A lot of people think that if I have a query that, say, grabs 10 rows and has the update skip locked on them, that what'll happen is as I fetch the rows, I'll only lock them as I go. So multiple sessions could both use skip locked and happily get, this one gets the first row, this gets the second row, this gets the third, as they fetch continuously. That's not how skip locked works. What happens is if this person tries to fetch 10 rows, they'll get all 10 rows and they'll be all locked. This person tries to fetch the same 10 rows with skip locked, they would simply get, I fetched no rows. So it's important to realize that skip locked really is going to work when you have a batch of rows that you have available first that aren't locked, and then piecewise you actually check each row to lock it, and if not, you skip lock to avoid it. Similarly, if one session does select star from table for update skip locked, and another session does the same, they won't be able to intermingle. This first one will actually lock all the rows in the table because that's what a select for update with no criteria does. The second one would simply get no rows selected. They would simply see none of the rows because they're all locked, and skip lock simply bypassed them all. So that last example, that last piece of code there, which you can obviously see later on when we look at the YouTube video in hindsight, is clearly that. The concept of have some rows first, which are retrieved without locking. So multiple sessions could all have a similar batch of rows they're looking at, but then pick each row at a time, try lock it. If you lock it, you're successful, you're good to go. If you skip lock, then you haven't blocked anyone else and you're not going to be blocking yourself. Hopefully that all makes sense. Dennis has put something on the chat line. Maybe it's easy just to try generate a random number and try and set their own if you have a unique key violation. That's true, but I perhaps should have put a demo here with multiple sessions, but it's bit tough in the hotel room. That won't work if two people try and insert the same random number. So the second session won't get a unique key violation until the first person is committed. And what happens there is then you could obviously have increased latency. You're right though, if you are absolutely confident that sessions will consume and commit their random numbers incredibly quickly, then you are insulated to some degree using that. For update, skip locked, and fetch from with a limit, that's from Ludith. No, what will happen is when you open the cursor for update, skip locked, all records that match your criteria will be locked. If another session does the same thing, even if you're just doing fetching, what's going to happen is the open select for update, skip lock will lock all the rows straight up. You actually have to get the rows without locking and then incrementally do a skip on. But thanks for asking that question. 19C, automatic indexing. Oh, the time's running away from me. This actually came in. I deliberately put this question in because it actually came from one of the attendees that at a city I've just been talking about, which is super cool. I was at your talk in Chennai on tips and techniques. You mentioned automatic indexing, but did not cover it because it was not a 19C features talk, which is true. We did a tips and techniques talk, but I mentioned 19C automatic indexing. That's really, really cool. And then I said, we're not going to talk about it because it wasn't a 19C talk. And I would imagine most people in the world, including those on this call, are not yet running 19C in production. You also said that adding an index was high risk without explaining why. Can you explain more on all of this? There are two common scenarios that you have to tackle when you're looking at adding an index. And this is the first one. That's relatively straightforward. And that is, you've got a query that's running for a long, long time. You've looked at the plan and an alternate or different indexing strategy may assist. Or this is the second strategy. Someone phones you, a developer, for example, and says, I need an index on the sales table. Your response is, in production, that table is 6 terabytes. Are you really sure? And often the response is, I think so. Now, that's not me being critical of people that request indexes. I have a lot of sympathy for developers. I'm being one of them nowadays because we often have 6 terabyte production databases and our poor developers get told, there's your 1 gigabyte development database. You're going to need to make sure your code's going to run fine when it gets to production. It's a tough deal being a developer nowadays when you don't get realistic database sizes in non-production environments. But that tends to be the way of the world nowadays. We tend to throw code over the fence into production and then try work out if it's going to perform well. So I have a lot of sympathy for developers in trying to work out when they should add indexes without actually having access to realistic volumes of data. Either way, there are our two scenarios. In either scenarios, and I'm just as guilty of this as anyone else, what do we do if we're in charge of those databases? We generally put the index on and see if it works. We sometimes have a little bit of cautious about it, but generally what happens is there's a piece of problem code, put an index on, is the problem fixed? Great. Now we'll deal with any fallout if it's going to occur. That's the part that really comes back and bites us because my view is adding any index to a database is enormously high risk, so much more high risk than people tend to think it is, because we generally add indexes to the really important tables in our systems. And where are most of the queries run on our database systems? Well, surprise, surprise, on those important tables. So if I have 500 queries that run on a table and I go add an index to solve a problem with one of those 500 queries, what I'm also doing is potentially changing the performance profile of 499 other queries. They may get faster. They may stay the same, or they may get worse. But that is an enormous risk to take something which is literally a sledgehammer I'm fixing one problem and potentially creating 500 other problems that then have to be fixed in an emergency fashion. Now, there are ways of getting around that, and that was why our tips and techniques talk in India was about using various structures inside the database to avoid that. We'll do that in another office hour sessions maybe. But I said, someone then asked the question, well, if adding indexes is so risky, what about this automatic indexing in Oracle 19? So let's step back and say, what is the best practice? If I was a DBA and I was going to really not introduce risk by adding an index, how would I do it? Well, I came up with a 10-step plan. This is in theory what we should all be doing. And rest assured, I fully acknowledge that none of us do, including myself. First, we would monitor the SQL workload. we would use some mechanism of gathering a large set of SQLs to work on, because just because we have one problem SQL, if we're going to do a lot of effort to work out whether we're going to add an index, we may as well do it efficiently. Let's go get the worst 10 SQLs or the worst 100 SQLs, etc. I could use AWR or top SQL reports or homegrown scripts to do that. That gives me a candidate set of SQLs to look at. Then I would consider indexes across, let's say I chose the top 10 worst SQLs. I would then look at whether indexes are going to be of benefit to those SQLs. You know, some of them might just be entire top to bottom scans. So some of them I can simply throw out, but for those that have predicates on them, I can now go analyze them and decide what indexes are already there and what indexes may be better if I could add them. Obviously, I'm looking at the predicates, looking at the columns that are referenced there, and that would become the leading columns of indexes. Then I have to sort of go through a consolidation exercise. And I put some very simple sort of mnemonics there on the right. You can see, what if I had a table which had predicates on column A, another query that had predicates on column A and B, another query that had predicates on column A, B, and C. I wouldn't go create 3 indexes on a table where I had predicates like that. I would simply create one index with all 3 columns in there, because it would probably serve the need of both the other 2 sets of predicates as well. So my point is, once I've identified some indexes to add or predicates of interest, I then have to go through a consolidation exercise, because obviously the less indexes I can add, the better in terms of space, backup time, etc., etc. Now, at that point, this is where often we would then go create an index. We don't want to do that because we don't want to introduce risk. So what I would do is, the best practice would be you would create them in either unusable or no segment mode. And whichever way you do, what you're really doing is creating just a data dictionary definition of that index, not the true index. It can't be used by the optimizer as such in terms of a genuine execution plan, but having the definition there lets us do things like ask the optimizer, if that index really did exist, would you be able to use it? And that lets us on to step number 5. I would tweak, for example, some hidden kernel settings to say, let the optimizer use, and when I say use, I mean it for an execution plan, not at execution time, use these data dictionary only defined indexes. Because just because an index was to exist doesn't mean the optimizer would even pick it. So we need to actually do a validation check here to see if the optimizer would actually pick the index as it exists now in just a data dictionary form. If there are some of those indexes actually the optimizer probably would pick, then we could actually now go ahead with confidence and actually create that index. Now, clearly we don't want to once again activate that index because we haven't really guarded against risk yet. I would create them now as real indexes. I actually spend the time of actually burning resources to build them, but I'll still create them as invisible, once again, to keep that impact risk down to 0. Now I'd take my 10 SQLs and actually run them, because just because the optimizer says it's going to use an index doesn't guarantee that SQL is actually going to be better. It might be worse. So I actually need to take those SQLs that I've identified, run them with the invisible indexes, and see if they actually get better. And we'd measure how long they take, etc. At that point, we're now ready to make a decision as to whether those indexes were any good. I've created, say, 3 new indexes. I've solved maybe 10 SQL problems, etc. But some of those indexes might have made those SQLs run worse. So I need to have a decision point here as to which indexes I will keep, which ones actually weren't of any use to me. And this is the cool thing. What if I get this problem of, well, 3 SQLs got better, but 7 got worse? Does that mean I just abandon it and say, well, let's just leave it? Ideally, what I would do is take the time to use SQL plan management. In that way, I would say the three SQLs that did run better, I'll leave them untouched, because just by seeing the new index, they're going to run faster. The 7 SQLs that are actually going to run worse by having those new indexes, I'll take their existing plans that didn't have the new indexes, put them in SQL plan management, lock those queries down such that even when the indexes do come into physical being, they won't get worse because they won't use them. Having done all that, steps 1 to 9, finally, I can make those new indexes visible. And what happens is the SQLs that will benefit now run better. The SQLs that would have regressed are unchanged. And I've done it with almost no impact risk to the system. We're done. Hands up who does that every day in their databases. Yeah, I put my hand up, and that's a total piece of fiction. I don't think anyone does, but it's best practice. What we should be doing is DBAs. And in fact, what would happen is you would then go grab a coffee after that enormous ordeal of all the work, and then you would start again, because the world keeps changing. You now have a new 10 SQLs to work at. So ideally, that's what you should be doing. Should be doing here for your databases 24/7. Dennis has got a comment. Exactly. In fact, Dennis has made the point here that adding index should be a last resort. And I'm so glad you said that, because here comes a shameless plug. I've recently been doing an Oracle Magazine article series on SQL tuning. And the first 2 articles don't even talk about tuning SQL. They talk about, first thing, look at, does it meet the actual business requirement? Is the SQL functionally correct? And the second thing is the SQL syntactically correct? A lot of SQL performance problems are, I didn't put the right brackets in, I forgot a join condition, etc. So thanks for pointing that out, Dennis, in the sense that, yes, adding to this thing about indexes being a risk, often we can solve SQL performance problems just by actually correcting the SQL, as opposed to actually going and changing database structures. And of course, the marketing spin for 19C automatic indexes is, what if we could do all of those 10-step processes for you? And the answer is yes. We actually follow that best practice I outlined there. It's not like automatic indexing in 19C is a DBA in disguise. It's not lazy like us DBAs. It won't just throw an index on and see what works, see what doesn't. It literally does that 10-step process. And this graphic is one you'll see in a lot of presentations from Oracle people, if not already. And that is the pentagon of automatic indexes. We monitor workload. We identify the indexes, but create them such that they won't impact existing work. We actually verify the validity of those indexes, make sure they will genuinely make things better, make a decision, make sure no one's going to be impacted using SQL plan management. And also we monitor the indexes as well. This is one thing I didn't say in the 10-step process. Once those indexes are on there, we don't just say, well, our work is done here, we can forget about them. We actually go monitor them over time. And the entire infrastructure is hopefully being able to be controlled just with the DBA having to set some preferences. And these are the preferences that come out of the box. I could talk about most of them, but I'll just touch on 3 for the time being. The second last one, auto index mode. That's an ability to have automatic indexing enabled, but not actually do any work. It'll do the monitoring, it'll do the various testing, etc., but it won't actually build and activate indexes. You can put it in reporting mode. So that's obviously a nice cautious first step when you're playing with this technology once you get to 19C. And the other 2 are auto index retention for auto, the third one, and auto index retention for manual, which is the 4th one. As I said, once we've created an index, we will actually monitor them to see if they're still being used, because why have an index on your system if it's never used? It's just burning up space and extra redo and hurting DML. So in that case, the automatic indexing will also watch for indexes that are not being used and get rid of them over time. Index retention for auto means that we will get rid of the indexes that we automatically created at some stage in the past. Auto index retention for manual obviously sounds a bit more alarming. That is, we will get rid of indexes that you created or we created manually as DBAs. By default, my understanding is in the current version of 19C, that is set to infinite, as in we will not actually touch any of your manual indexes. For the auto, I think it's set to 90 days. It may vary from platform to platform, or patch level to patch level. So we might look for an index that hasn't been touched for 3 months, and therefore if it hasn't been touched, then we will drop it. Your requirements should drive what numbers you set that to. If you have some indexes that you know are used once a year as part of the annual report, then obviously you'd probably set those values to at least more than a year, but you have that control over it. So that's automatic indexing in a nutshell. Unfortunately, because I'm traveling, I can't actually show you some real demos of that. My 19C, in terms of running with all the bells and whistles, is running on the home computer. I do have a 19C VM on this one, but it's not kitted out for automatic indexing. But maybe in another session, we'll actually look at some real examples of that. Memoptimize. Oh, I feel bad about the career advice. We know I get to it. We might have to do it as a dedicated office hours session. Memoptimize. This was a simple question. Can you explain what memoptimize does in 18C and 19C? Let's talk hardware. And we'll see where hardware comes into memoptimize soon. Back in the day, when you bought a PC in the 80s, 90s, they had a thing called a front side bus. This is, when I went to university, we learned about bus-based computers because that's generally what computers were. And that is, you had this sort of thing that ran along, for lack of a better term, the middle of the computer, and everyone shared it. If a CPU needed to talk to memory, it would talk via the bus, hence the name bus. It's like jumping on the bus to get somewhere. If a CPU needed to talk to disk, if CPU needed to talk to network, anything needed to talk to each other, it worked along the bus. So the bus was the bottleneck for just about everything in your system. And that's why computers generally ran pretty slow back in those days. No matter how the CPU technology and memory technology got better, you were limited by the bus speed. AMD, saviors of the universe. No, not a sponsored post for AMD. Invented a thing called Hypertransport, which was the concept of attaching some memory directly to CPU, such that CPUs could at least access a subset of memory incredibly fast. And also they improved the communication lines between those CPUs using this thing called Hypertransport. That's why, this would be what, early 2000s? Do you remember Opterons? Opteron servers were the absolute bee's knees when it came to running databases. They absolutely flew. They were using AMD chips. Intel said, that's pretty cool. And obviously we came to the Nehalem architecture, this circa 2007, so it's been around for a long time. And the concept is very similar. Fast connections between CPUs and memory being aligned with CPUs to access it very, very fast. To prove that to you, we now know that hardware is just crazy fast for good code. So let's look at an example of what I mean by that. We might run a touch after the hour, but hopefully we'll get this done. Let's prove to you how fast hardware is. I'm creating to my local database here. I'm creating a table, just a very simple table with an integer date and some varchar 2. I'll run some code to see how many rows per second I can pump into this table on this little baby laptop. Hopefully the timing is about right here. It's hard to guess how long this will take because I'm obviously running parallel streaming and recording the session. But this laptop, about 1200 rows per second. That's not too shabby, but obviously it's a laptop. Let's now connect. You can see the top line there. I'm connecting to a service here called aura_cloud. Maybe a bit more juice behind the scenes. Create the same table, run the same demo, let it run for a while. And now this time I'm getting, wait for it to finish, obviously something significantly better. I'm getting 24,000 or 25,000 rows per second. And obviously we can take these things to extremes. I'm connected to a new thing called exacloud and same table, run the same code, and let's give it a run. And now that I'm connecting to that, I'm getting 1,000,000 rows per second. Now, at which point you're going, that's all well and good, Connor, but what on earth is exacloud going to cost me in terms of fees, licenses, etc.? I can't just keep throwing bigger and bigger chunks of hardware at things. Well, let's look at the tnsnames.aura file on this machine. You can see that DB18PDB1 is localhost 1518. It's this laptop. Aura Cloud is, guess what? This laptop, localhost 15. And exacloud is, yes, this laptop as well, localhost 1518. I didn't change any hardware. I simply changed the quality of the code that I was running. And yes, this 3-year-old $800 laptop can put in 1,000,000 rows per second into an Oracle database. Hardware is just ridiculously good nowadays. What's the point of this? Let me go back to our other share. My point is great code always wins. Great code trumps any kind of hardware. If you write great code, you can write incredibly cool and fast ingest of rows into a database. And guess what doesn't write great code? IoT devices. IoT doesn't tear. The benefits there are that let me get to 1,000,000 rows per second with things like bulk binding, array inserts, doing all these kind of things to avoid doing the worst kind of operation in an Oracle database, which is one row commit. The problem is that's exactly what IoT devices do. They're very simple. They're fire and forget. I picked up a reading, fire it off. I picked up a reading, fire it off. It then becomes the application coder's problem to work out how to get that into a database efficiently. Maybe they hold off inserting and batch them up and send them in bulk. but then you've got things like timeout issues and how big the batches do I make. It's complexity. And so many people go, oh, one row inserts seem to be slow. I need Mongo. I need some other technology, etc. Well, the reality is, I think all of that's false. Wouldn't it be nice if we could have these IoTs just fire and forget rows at us, and we can still get the benefits as if we'd rewritten the code to do batch inserts? And that's one of the cool things in 19C. Let's have a look at it, because I haven't had time to install 19 Windows yet on this laptop. So hopefully we can see that. I'm going to create a table with the primary key on it. I'm going to do a test here, just a normal insert test, 250,000 rows. I'll set that running because we may have to talk amongst ourselves here. It took about 35 seconds when I did it in isolation today, but as I said, we're recording this session, we're streaming out over the network. It may take a bit longer, but we can look at the code there. We see line 3 is an insert and line 4 is a commit. This is a one row at a time with a commit insert operation, mimicking the kind of data we're going to get from IoT devices just being flung at us fire and forget style. Maybe I could tell a joke while we're waiting. Either way, 29 seconds. We took 30 seconds to do it. And obviously that might not be sufficient if we've got thousands of sensors. So, nowadays water bottles tell you when they're empty, without even looking to see if they're just empty. So many IoT sensors sending us information. Let's truncate the table and look at the 19C feature called memoptimize writes. So I do alter table, memoptimize for write. That's just a dictionary flag. And then I need to use a special hint. You can see there, insert memoptimize write into the table. But it's the same operation, 200,000 inserts, one row inserts. Oh, I haven't actually set it running. Let's set it running and we'll see how long it takes to run. So remember the first normal conventional inserts, 30 seconds. This one, less than 5 seconds. And generally my experience has been somewhere between 4 and 6 times faster. You might also notice here, there's no commit. You might be thinking, oh, maybe this is a cheating demo because we're actually just doing it all in one transaction. What memoptimize writes do is let you fire those rows one at a time to us. We will store them in the memory structure in the database. Effectively, we're on the fly writing the complicated code you would have to write to batch these inserts up. And then what happens is in the background, we simply drain those rows down to disk in a nice, efficient batch style operation. Because of that, the concept of a commit actually doesn't really make sense because to literally fire that row, we say, yep, we're done. It actually hasn't made it to disk yet. It hasn't made it to the data files. It hasn't even been logged. It actually has just been put into this memory structure. And then when we drain it down to the data files or drain it down to the table, that's when you will actually see the actual read logs and cost being taken, but it's taken away from you. It's done asynchronously. Important to realize, what does that mean? Yes, there is the chance of losing data if you had a system crash during one of those batching events where you drained information down. But that's what IoTs are all about. Sensor readings are, here's a billion readings, one row at a time. Look, if you lost 5, lost 10, lost 100, I don't really care. I'm just sending them to them as fast as I can. So this is for data that needs to be ingested incredibly fast, and you are prepared to potentially lose it if you were to have a system crash, which obviously is fairly rare. But you get this wonderful thing of actually seeing a lovely performance benefit of actually being able to have rows inserted very, very quickly. Now, someone has put on there saying, can you repeat the first block also without the commit? I could, but I would have to write it, and we're running out of time. In fact, we're almost out of time already. It obviously will be faster than 30 seconds, but it isn't really then a representation of how an IoT commit would actually come in. IoTs are one row and actually just commit it straight away. So that's what I'm trying to mimic here. I hope that makes sense. Now, if people are prepared to stay on the line a little longer, I know I say that every month. We'll look at the memory read test as well. So as I said, IoT doesn't care about writing code great, and obviously neither does bad code. The same kind of thing that pushes information in one row at a time. One of the things we're obviously seeing in the world of ORMs, and no, I don't want to be critical of ORMs. One of the things we're seeing in terms of CRUD style code is a lot of primary key lookups when things like set-based operations would be better. Now, we could simply jump on our high horse and say, no, those one row lookups are bad. You should just be, you should rewrite your code, but that's not really the world we live in. Sometimes we have to just take those one row reads and try and make them faster. And that's what another operation has come in terms of 19C. So let's go back to our share. This will be our last demo for the day because we're out of time. So I'm going to create a table called T. I'm going to put in 10,000 rows and gather stats on the table. It just looks like a normal table. I've put this hint in there called special. It's not really a hint. It's just simply, it's going to make it easy for me to look up that query in VSQL later on. I can simply query for it. But let's look at select special from T where X equals 10. X is the primary key. It's just a primary key lookup. And we can see that from the execution plan. It's going to do an index unique scan on the primary key index. One little cool thing here in 19C here, which I'll simply digress on, is notice that we also get this thing called a hint report. It's showing us that the very last line, it says E-special. E stands for error. It says you have a hint called special. That's not a real hint. That's an error. So this is the nice thing of getting some nice information about the hint quality in your SQL. As we said before, I'm just using special to make sure I can find it in VSQL. Ah, no, I've run out of memory. Oh, let's give it a run. So let's now run this query. I do select from T where X equals 10. It did 120 consistent gets. Now that's obviously a lot for a primary key lookup. Most of that is the cost of parsing. If I run it again, we get something much more what we'd expect. Primary key lookup on a relatively small table, 3 consistent gets. Probably root block, leaf block, table lookup, 3 consistent gets, or branch, leaf, etc. So as we'd expect, to get a one row lookup in a small table via an index is 3 consistent reads. If we go look in VSQL, we can actually see that we did 3 executions, 126 buffer gets, 120 for the first execution with the parse, and then 3 for the next run and 3 for the run after that. So it's 3 buffer gets per execution from that point onwards. Let's flush out the share pool, drop our table. Now I'm going to create it with a new syntax. This is segment creation immediate memoptimize for read. The important part actually is memoptimize for read. There's a rule in the documentation that says if you want to read memoptimized table, it must be created with segment creation immediate. Normally, tables actually don't come into physical existence until you put the first row in them. And that's what's called segment creation deferred. That's the default. So memoptimize for read only works if you actually say, even though the table is empty, go allocate some space on disk for it and give me an extent. I insert the 10,000 rows, collect stats as before, then I have a new operation to do. I need to populate that table into the memory optimized read store. Once that's done, once again, let's look at the execution plan first. It's slightly different now. If we look at line 2, it's an index unique scan as before, but it says it's read optimized. We're using a different mechanism. We'll be querying information direct from a memory pool as opposed to the index itself. Let's give it a run. The first run is 407 consistent gets. There's a little bit more work going on here to work out how to best run this query for the first time. There's a bit more parsing overhead. But then next time I run it, you can see that the key line consistent gets, no consistent gets. It literally doesn't access the buffer cache anymore. It directly accesses this memory structure. That's really cool because A, it's less work obviously, but also every time you do a consistent gets, you've got to protect that request into the buffer cache with things like mutexes and latches. In this case, we don't have that overhead anymore because we're not accessing the buffer cache. In fact, it's continuously that many. If I go look at, oh, I've hit one too many returns here. Let's go back to where I've got the query from VSQL. Hopefully you can remember that the first execution used 409 consistent gets, but I've got 3 more executions and that consistent gets has never gone up anymore. And we're still buffer gets is still 409. So what we're doing is now is all subsequent executions actually have a cost of 0. At which point you're thinking, cool, I'm going to go out and get all my SQL that's in my PL/SQL blocks like this one. And, they'll be fantastically fast as well. That's awesome. This is what you'll see in VSQL. This is the one that was run outside PL/SQL, 4 executions, 409 initial buffer gets, and none from that point onwards. And guess what? We get a second cursor. second child for our cursor. 1 execution, 14 consistent gets. That's the one I ran from PL SQL. What does that mean? Yes, PL SQL cannot use the memory optimized read store as of this current version of 19C. I don't know if that's planned to change. My hypothesis without proof is that the implication here is, or the intent is, that if you're running SQL from inside PL SQL, it's already incredibly close to the database. So the benefits in terms of efficiency might not be as great as if it was coming from, say, a JDBC or some other external driver. That's my hypothesis. It may just be an implementation restriction we're hoping at looking at. Now, I have seen some questions coming in, but I know we're running over time, so I'll take those offline and write a blog post about them, etc. Let's go back to the slideshow because we've obviously missed a fair bit. But we're 10 minutes over time. So I hope you've enjoyed the session. We didn't, as always, cover everything that I want to do. I just need to talk faster or talk less, or people need to interrupt me more and tell me to move on. We'll see how we go. But as I said, there's my blog, my YouTube, my Twitter. This entire session will obviously go on YouTube at some stage in the near future. But for now, I'm going to watch the sunset here at Pune. I'll give you let me stop this share and I'll give you a last look at Pune. The sun is getting ready to go down. Beautiful day here. We do a talk tomorrow. Thank you very much for joining me on office hours. Hoping me moving the camera doesn't make you feel seasick. Thanks very much for your time. Great to have you on as always, and the rest of India for me. And I'll see you next month, hopefully back in, next month I'll be back in Perth, and the office hours after that might come to you from South America. Bye for now, everybody.